Okay, we are ready to start. This is the last talk of the workshop. Last but not the least, we have Csaba Szepeswari from University of Alberta, who is actually currently at DeepMind in Google in the UK, or you're back in Alberta.
I am back in Alberta since about, I don't know, more than a month ago, actually.
Oh, okay. Well, in both places. He's
Yeah.
doing very interesting work in reinforcement learning and machine learning, and he's done fundamental work in the area. Some of his older work on Monte Carlo tree search actually has been used in many places and recently won a Best of Test of Time award. So we're very excited to hear what Csaba has for us. Thanks.
Thank you. Right, so this is the last talk of the workshop, and I don't know what even to say. Like, thanks for staying, first of all. After the talk, I will need to leave shortly after to the airport, but I'll try to hang around just a little bit more. But just as a heads up that I might need to, at some point, just leave. But I'm, of course, very interested in talking to you if we'll have time for that. If not, then, like email, all the usual channels of communication. Anyhow, so this talk is about recent work that I've been doing together with wonderful collaborators in Google Brain, Berkeley, and Yasin, who knows where he is. Okay. Next slide, please. Okay. Microsoft PowerPoint is not responding. Thank you. All right, that's fine. All right, so just to start, so I'm going to talk about, oh, yeah, there we go. I'm going to talk about model-free RL and my way of trying to make sense of what is going on there. So we have seen what's happening. All right. Is this self-play or? All right. Microsoft's playing tricks with me. Yeah. All right. So I knew that I should use whiteboard. Technologies. Yeah, I know. I'm just wondering about whether it's going to play other tricks on me.
Probably. Let's go, man. We're
All right.
injecting noise. Tom, we're injecting noise in your slides. Exploration.
Yeah, okay. Unknown territory, robustness. Okay, so we've been a bunch of results which were unexpected and coming from the combination of model-free RL techniques with deep learning. I can say at least that I didn't expect some of these results, and it would be nice to understand when these techniques work and how they work and what their scope of applicability is and whether we can improve them, right? So that's my goal in this talk, and that's the goal of this work. And so this slide is just used to contrast this model-free world with the model-based work, where we can also see MO there. And there is a lot of scope for both of these methods, but it seems that there is some nice corner. Maybe it's the large sample regime, but for model-free methods. But I guess it would also be important to reduce that sample complexity, right? So if you see these ridiculous sample complexities, or not sample complexity, but it's like the need for the compute, it's a ridiculous amount, then you must be wondering about whether there is a more efficient way of doing things or not. So that's what I'm after here. So anytime in the talk, please, if you have any questions, stop me. So this is just a notation. I'm not going to use S for states. I'm going to use X. Right, and then I'm going to use A for actions. Yeah, it's like, just because I want to be a contrary, right? I don't want to follow any trends, right? Okay. Yeah, it's like if it has to be that like that, then it has to be that. Okay, so I'm going to make some assumptions here, and you might think that like they're innocent, but I don't actually know. So the state space is going to be countable, and that makes certainly easier to write certain things. Action space is going to be finite. I think I do have ideas about how to go beyond finite actions states, but the countable state space is going to be important at one point. It's kind of ridiculous. There's probably some way around that, but we'll come back to that. And to reflect on the first day's talks by Ben, I care about a case too, when maybe you don't observe, like the states as they are, like enumerated or whatnot, but you have a high dimensional observation, and maybe it's invertible, so there is no state aliasing going on. And you want to control the system to minimize the cost, and you care about the regret compared to like some other controller controlling the system. Maybe not the optimal controller. Maybe that's just too much to demand, and we'll see how that plays a role. So that's kind of the setup. Yeah.
So the comparison is to what? Like it's a different set of states?
Right. I mean, like it's a different controller controlling the system, so it's like a different sequence of state actions.
So you define a set of controllers and you're comparing to the base one?
I'm going to, like, it's like an individual regret bound, if you wish, right? So you want to be good against all possible controllers, but against some controllers, inevitably it will be harder to compete with them, and I want to see the dependence on the choice of this controller that I'm competing with to show up in the regret bound, right? It's like a non-uniform bound, if you wish. You can make it uniform. Like, the game is that you can make it uniform if you start to make strong assumptions about the environment, but okay, why? Why do you want to do that, right? So maybe a non-uniform bond is just good enough. All right. So this is great, but and it seems that like we are almost back to the tabular setting, but I actually don't want to do the tabular setting here. I'm really interested in when you throw in the neural network and you use the neural network for value function approximation, and I will try to make an effort to understand like what can you say about these model-free algorithms in that setting when you have this neural network in the picture that is approximating the value functions. So that's why I can allow high-dimensional observation space, because I'm hoping that the neural network is going to take care of that, right? And I will make this quite formal, actually. I wish I knew how to go to the next slide in a seamless fashion. This is not how. All right, this is going to be painful. Just going to the next slide. It's not working very well. I have an idea. No, I just put this on and then. All right. Eventually it worked. Okay. All right. So let's start with some basics. So you can have these policies. They induce distributions over trajectories. And I'm going to be interested in, the total cost, and that's somehow related to the average cost setting. So I'm going to use the average cost setting for writing my equations. So lambda of pi is going to be the long run average cost of running policy pi against the system. and value function. In a simple case, it's just you just offset the cost with the average cost, and if you start a system from a given state, it gives you a value, and you can make it an action value function, and they're related to the value function, and the action value function satisfies an equation which is just a linear equation in the average cost setting under proper conditions. You can show that this holds, right? Okay, so they're just getting the formalism out of the way. So people have seen the Bellman equation, and this is just to brief you about my notation. Any questions? It's good? All right. I forgot that I have to push the... Why? This has something to do with projection, because I tested these slides without projection. Anyways, okay. So before you jump into proposing an algorithm, maybe you should look at the objective that you're trying to control. In this case, we are trying to control the regret. And it turns out that there is a very easy way to decompose the regret if you bring in the average cost for each of the policies that you're executing at every time step, right? So this is just like almost a standard decomposition. So you can add and remove terms. So then you see that there are three terms that you need to control. So the first term I'm going to call the pseudo-regret. So that compares the average cost of the policy at time step t with the average cost of the competing policy, right? And then there are these other terms which are comparing the running cost with the average cost, and the same holds for the same type of terms for the competing policy, the policy that you want to compete with. And to control these terms, one thing to note is that you need to convert, since you brought in the average cost, you need to converge to the average cost. You have to let the system, converge to its stationary distribution or whatnot. So you might not want to change policies too fast. So the way to control that is going to be to use phases. And then if the phases are long enough, then that term is going to be well controlled. So I'm not going to worry about that term too much. Just keep in mind that you will need to introduce some phases. And there is some cost for changing the policies too fast. The last term that's completely obvious.
Maybe better think of those as transients rather than noise.
Yeah.
Is that right? So this is the transient behavior before state state. Okay.
Right. I mean, it's both noise and transients. If you want to talk about high probability regret, then there is additional noise on the top of things. But yeah, it's kind of the same thing.
Even a steady state.
Even if there was no noise, the transient behavior has to be washed out. Okay. But I'm willing to make assumptions about like fast mixing at this stage, and just to simplify things. And so I'm not that much worried about and those terms. The only way you can you control that term is basically by introducing these slow changes to policies, and we're going to do that anyways. So the last term, it's out of our control, so let's not worry about that. So the first term, so that's the term that we need to control. And yes, we can control that term. Maybe the whiteboard would have been a better choice. All right. So that term can be controlled if we recall what's called the performance difference formula. This is pretty ridiculous. Switch machines? I don't know. Or end slideshow, restart, maybe. Oh. All right. So here we come. So the big help for dealing with the pseudo-regret is this performance difference formula, which I first read about. I think it was Shamstadis. But there are some, wow, okay, look at that. No! This is a nightmare. Why? There's huge lag, but I'm plugged in.
Why don't you use your laptop?
Okay. I can try.
Charles, I think sometimes PowerPoint has a delay, like just in the slide advance,
Oh, that's probably right.
like 10 seconds or something ridiculous.
It seems that
Is that in a setting or?
I don't use PowerPoint, I gotta do it once and I left forever.
Thank you.
Did you export the PowerPoint to PDF and then use the PDF reader?
Slideshow.
It seems like it's loading your.
This is not even just.
This looks like everything. Try moving back to me.
Yeah.
There we go.
Just have to restart. So the performance difference formula tells us that the difference between the average cost of two policies can be expressed as this formula there. So here I'm using this inner product that just means that you're averaging over the states with respect to the stationary distribution of the second policy, and you're comparing the differences between the action values of the two policies. So one policy, the first policy and the second policy. So the meaning of these terms is that, well, I should probably not touch this thing because who knows what it's going to do. So the meaning of this notation when I plug in the policy in the second argument is that I'm just taking an average with respect to the state distribution at the given state according to that policy.
What is mu?
Mu is the stationary distribution under pi star, which I assume to exist for simplicity. Okay, so this is a very nice formula. You can rederive all of dynamic programming based on this policy iteration, everything. It's very, very nice. What's important for us is that this difference in the action values is a linear expression in pi. So here in the second argument, when I plug in pi, so that's just like an average with respect to the distribution that the policy induces. And if you plug back this difference formula into regret, and you write out what these inner products mean, what you say is that for every state, if you want to control the regret, for every state, you should be controlling this difference here. Okay? So this is the action value that you get if you execute your policy and the first action is according to your policy. And this is the action value that you get if you execute the policy, but only from the second step, and the first step is according to pi star. So there is one step difference between two. So this is really nice. It seems that we only need to care about controlling this sum for every state. Easy, right? Until you realize that the problem is that by the time you have to choose pi of t, the policy that you're going to execute at time step t, you have no idea about this function q of pi t yet, right? Because that depends on the policy. So you want to keep this small, so how can you keep it small? You don't have access to the system. You can't really compute this whole expression. It seems that like to control this term is almost as hard as solving the full problem. So it's a chicken egg problem. All right. But here comes online learning to our rescue, and we have heard about online learning a couple of times before. How many people are familiar with online linear prediction? So just briefly, there is a learner and an adversary, and the adversary is choosing these loss vectors, and the learner has to choose one of the components of the loss vector in every round. And the learner's job is to control the regret against any choice of a component in hindsight. Okay, so even against the best choice in hindsight. And can we even do this? It happens that this kind of just models like it's a glorified and crystallized model of an IID word. It's like a generalization of IID, but it's not as hard as you might think, because you need to compete with the best single decision in hindsight, and the adversary doesn't have that much of a lever on you, because how can they make your job really hard to predict what to choose? Well, they can make the environment random, and that's it. Right? So in a way, the worst case environments for this setting where you need to control this regret are the IID environments. Of course, here you're not making any assumptions about the sequence, and the sequence can indeed be chosen in a closed loop fashion by the adversary. So the adversary can pick, well, cannot use your most recent decision, but it can use the previous decisions when it comes up with losses. Okay? So the adversary can be reactive. Right, and so what is the algorithm to use? Well, there are many algorithms proposed. They come under very many different names. Exponential weighted average forecaster is one name. This is also an instance of follow the regularized leader. This is also an instance of mirror descent, and there are many other versions of these algorithms. And what is known about these algorithms is that they can control the regret, and you can get results like the following, which is taken from the book of Nicolo and Gabor. So this says that if you're properly tuning this exponential weighted forecaster, which is just, okay, in reinforcement learning would call this the Boltzmann exploration policy, then you can control the regret in a sense that the regret is going to be sublinear. So the average regret per time step is decreasing by time. So that's great. So you can get the square root T regret no matter what the adversary is. So how can we use this? So the way you can use this is that, well, we had this problem, and that problem, I told you, is just a linear prediction problem in disguise, right? So when you're plugging in pi t in the second argument, that's just like an average. So it's linear prediction. So you can choose, based on this, based on what we have learned on the previous slide, you can just choose the exponential weighted average forecaster and use that as the policy. And if you do that, then remember what I said, that, well, you don't want to change the policies too frequently or too fast. On one hand, because you need to control the second term, and in the actual regret, and also because you don't actually know. So when you execute this policy, when you write this policy, you can write this expression for the policy, but where you get this action value function from, well, you need to estimate it, right? So one way of doing this would be to run the policy for a while, get some data, and then estimate its underlying action value function, right? So this is exactly what we're going to do. So we're going to run the system in phases, and in each phase we're going to fix a policy, and we run that policy, collect some data. Based on the data, we're going to estimate some action value function. So we're not going to have access to the true action value function, but some approximation to it. This is where the neural networks are going to come into the picture. I'm going to make some assumptions about what they can do. And once you have that, then you can plug in the estimated action value functions into the expression above and hope that the whole system is not going to collapse and is going to be stable, right? So obviously the neural networks are going to introduce some errors, and you might be worried about that those errors are going to compound and your system is going to break down. So that's the question. All right. Okay. So before we move on, so I need to know that I kind of like this very much because it kind of tells me why, if you read the literature, recent deep reinforcement learning literature, people are really obsessed about putting these KL penalties everywhere when they're updating their policies. And the explanations that I'm getting from those papers are not totally satisfactory, right? Like I don't quite get like why, like intuitively speaking. So one thing that they say intuitively, and that makes sense, is that you want to stay close to the previous policy, because if you stay close to the previous policy, then maybe you can reuse the old data and like you won't have any big surprises. But okay, so this is also telling me the same thing, right? So I should use something like Boltzmann exploration. Online linear optimization tells me that you have to regularize, stay close to the previous policy. So to me, this is like a nice way of trying to make sense of why people are finding that these regularization terms do help in practice. Okay, so what happens if we plug in this approximated Q functions is that, well, you got this expression in the regret that you need to control, and you can again add and subtract, okay, these terms. And once you do this, you realize that, well, you actually need to control the first term if the second two terms are controlled by the neural networks, like by how well you approximate. So the second and third terms are the approximation errors, the errors of approximating the actual action value function when you're running your value function estimation procedure. Yes?
Sorry, it just occurred to me, you're sliding something by, which is you actually have banded feedback, but you're learning a complete predictor and then treating the predictor as sort of complete feedback and running a full information, no regret algorithm on top of the model.
I do have trajectory-based feedback. I'm sweeping under the rug everything that is related to how we are learning the action value functions at the moment. I will come back to that a little bit later, and we're going to discuss some pain points there.
But no EXP3, like it's just fully observed, like exponential rates.
It's like once you postulate that you have a black box that can estimate action value functions over the state space in some error metrics, so we need to use those, or we better use those error metrics over there, then right. So then you just have to focus. The next step is going to be to focus on how to fulfill that promise that we'll be able to do that. Yeah. All right. So, okay. So in summary, how does this work? So if you put this together, everything put together, then it's like you can say that this is an actor-critic method, where you're going to have an actor which plays a Boltzmann distribution with respect to the sum of the previously estimated action value functions. And then you run this in closed loop, collect some data. The data is fed into this other box, which is going to be the back box. I'm worried about that these are not the most recent slides that I have, but anyways, we'll see where you go at the end. And then based on this, you learn your action value function. Let's say you use a neural network, and every once in a while, you update the sum. And then you update your policy. All right. Okay, so up to now, if we put everything together, then we can read out the following result from just putting together what we know so far. that the pseudo-regret of this algorithm is going to be controlled as follows. So if you have errors in approximating the action value functions that are epsilon for each of the phases, then altogether you're going to have some error that's 2 times t epsilon. So it's linear in that error, but that's OK, I say. Because that promises that as long as you can keep those errors small, that the term is OK, it's growing linearly, but like that's life. And you also have this other term where you see that if you have longer horizon and E is the number of episodes. So if you have many episodes, then that term is going to be smaller. And you have this other term, which I alluded to at the beginning, which expresses how hard it is to compete with the policy that you use as the comparator. Okay, so there is the term. It's a little bit hard to read. The last term, that's the stationary distribution of that policy. And the stationary distribution is integrated against the log, the square root of the log of 1 over the stationary distribution. This is where the countability of the state space somehow comes in. And probably there is some way around that, but this is the best that I could do. And you can upper bound that by the entropy of the policy. So if that policy tends to go to some small part of the state space, then it's much better than if it's spread out everywhere. If it's spread out everywhere, then that term can be really large. OK.
What's L?
L, where is L? Oh, L is the abbreviation of log 2 over data, because it didn't fit. All right. These are not the slides. These are not the most recent slides.
How do you estimate the Q values?
I didn't tell. I didn't tell yet.
Oh, you haven't told
I
us.
haven't. Yeah. All right. So can I just play around with the slides a little bit? Because these are not the slides I wanted to use. These are old slides. Sorry. I hope that the slides, the recent slides are saved. Like some. This is very dangerous. I think that these are, like, my slides were simply not saved. That's it. All right. So finally, if somehow you magically are able to control the errors such that after tau samples, your error goes down at the 1 over root tau rate, the error in approximating the action value functions up to some level E infinity, then you can optimize all the terms, the lengths of the phases and everything, and you can get a t to the 3/4 regret with all these other terms and the linear term at the end.
You have a linear term at the end.
Yes, you have a linear term. I mean, like, if every time step your wave function approximation is off by an epsilon, I think that the linear term is the best that you can hope for. Yeah. And so there, the hope is that you make the neural network larger. That term goes down. Goes to zero.
So, Csaba, how are you thinking about sort of So if you could approximate Q super well for every policy, you could kind of just do policy iteration or do some kind of...
Right.
So
So the
how-
question is whether this has any advantage compared to just doing policy iteration.
Yeah, how are you
It seems,
thinking about
well, this proof certainly doesn't go through if you try to do it with policy iteration. If you try to do something with policy iteration, I feel that you have to have a much better control of the errors. So intuitively, my intuition is that what happens is that you're going faster by being a little bit slower here. So you're summing up the previous action value functions. So every episode can be a little bit shorter because of that. So you have larger variance for every episode, but since you're averaging, that variance kind of washes out. And since the episodes are shorter, you can switch more often, and you try to balance this in a careful fashion, which if you do policy iteration, then I don't know how to do. Yeah, it's like a smooth changes, right? Yeah.
Can the term the 2 epsilon infinity, can it cancel out each other, the approximations? Because that is coming from the approximation error, right?
Yeah.
If it's not always biased towards...
Well, yeah, this could be pessimistic, but okay, I try to be optimistic, but sometimes it's just too hard.
Just to make sure I understand the setting. So this is so what's adversarial here?
There is
What's
nothing
the-
adversarial. I just use an adversarial argument to get a bound here.
Okay, and
Right.
So what's different than the online MVP? So
Next
where's the
slide.
theta 3?
Yeah, so the online MDP setting, I think let's wait for the next
Just
slide.
in terms of the setting, the assumptions
In
is-
terms of the setting, it's different, right? Because here, in the online MDP setting, an adversary actually chooses the rewards
Right.
in an arbitrary fashion, and it's you know the dynamics, and based on that you compute the action value functions.
So what is the algorithm know here, just to make sure we're on the same page?
So the algorithm uses a black box that it can feed data to, which should approximate action value functions,
And the word is static?
and the word is static.
And what changes from data? Is this just optimization, or is there anything changing?
It's a fixed MDP, nothing changes. The argument used the online MDP framework or the
Ah, I
same
see.
idea
So this is for
to get,
optimization.
yeah.
I see.
It's not really optimization, it's regret minimization, or I'm selling it as regret minimization. We'll come back to
But why
that.
do regret minimization? If you have the offline MDP and everything's static, why not just...
You don't know the
Yeah.
MDP. You need to run a policy to actually get a sense of how well the policy is
I
doing,
see.
right?
So
So it's the online setting.
So you're estimating, you're estimating the cues.
The action value function is being estimated. So remember, when I explained the algorithm, the actor is running for a while, it's collecting data, it's feeding it to this other box. That box is estimating the action value function,
Oh, I see.
which
So
is,
this is some actually on policy
it's
method.
yeah,
and
it's
estimating
exactly
the
an on
cues.
policy
What
method.
does on policy mean?
On policy here means that we only demand the action value function estimator to work to estimate the action value function of the policy that is actually generating the data, not some other policy.
It's online. Just that
That's okay.
But it does that globally well.
Yeah.
If
Well, in an L1 sense.
Right. So in
So it's
some
an
sense-
average, yeah.
Right. In some sense, the epsilon infinity is a function of the algorithm, right?
The epsilon infinity is a function of the black box. So my way of trying to deal with neural networks is that I just like close them off and I say that like it's someone else's problem to make this thing work, but to what extent? Huh?
This is not a question.
Yeah.
In some sense, if you're running on the trajectories that you see, if I never do action 1, you're
Yeah,
going to have a high error on
Right,
action 1.
Yeah.
So somehow epsilon infinity is a function of your algorithm and the way that it explodes.
Yeah, absolutely. Not even epsilon infinity, the whole rate and everything. So, next slide, or 2 slides later. It's a good point. All right, so here I just wanted to show some history of like this kind of the same ideas have appeared many times in the literature, right? Like this algorithm is very close to conservative policy iteration, which is a very different setting, but it's like the same idea. Sham and Jones been working on this. So there the idea is that you're changing the policies in a slow fashion. It's a different way of controlling that, and you do this to compute a near optimal policy in a different setting. But it's kind of the same idea. Here as well, you're slowing down your changes. Another thing that's even closer, which already came up, is this online MDP framework, where you think that an adversary is choosing the reward functions time to time, and you have access to the MDP, and you're able to compute the action value functions once you offset the rewards. So in every round, at the end of the round, you offset the rewards. Let's say you're solving the shortest path problem or whatnot. And so in that setting, so actually the tools and the techniques that are used in this work are coming from this paper, right? Like it's exactly the same thing. It's just like regurgitated in a different way for a different purpose, but it's like the same machinery. We noticed that you can do this when we were working on AQR problems, and we wanted to get model-free algorithms to work. Right? There is a little difference because the loss functions under proper assumptions, under nice assumptions about the system, are strongly convex. So you don't have to use Boltzmann exploration or any exponential evading. You can just follow the leader, right? And then you get better regret bounds there because the losses are strongly convex. So you can get this t to the 2/3 regret. And then it's also related to algorithms in the literature, in the deep reinforcement learning literature, like MPO, which it doesn't have any theoretical analysis or backing, but it seems to work pretty well. Like people are really excited about these type of algorithms. So that's kind of why this is interesting to me. And then we have this work. And there's a bunch of other works, of course, which I cannot go into. And it seems that my slides are, like, these are really, really odd slides. So I need to kind of reinvent myself against in the face of uncertainty. So one question was, like, why is this different than policy iteration? Good old policy iteration. And so I can't, like, this calls for a lower bound for that policy iteration maybe should be doing worse on some problems at least than Polytech, less control of the regret. And I don't have those lower bounds, but we were running experiments. And when we were running experiments, the obvious comparison was to replace the Boltzmann exploration with respect to the sum of the previous action value functions, just with the Boltzmann exploration with respect to the most recent action value function as the closest relative to this algorithm, right? So the classic, let's do Boltzmann exploration once you have estimated your action value functions. So this is on queuing problems, and the x-axis is number of phases, and the y-axis is the average cost for various algorithms. And LSPI is actually the exact same algorithm. This is linear function approximation. And my slides about how to, anyways. This is linear function approximation with the exact same settings. And what you see is that if you introduce this sum of the previous action value functions, you get a much more stable, much better controlled behavior, at least in these experiments. So it seems that there is a real advantage to doing this. It's not just like the theory is telling us that maybe this stabilizes this algorithm. It actually seems to work better. So here we are also comparing with another algorithm, RLSVI from Ian Osband and I think Dan and Zheng and Ben. and that algorithm is doing pretty well as well. So in some sense, like with some, so the different curves correspond to different tunings. Like we have a learning rate, this eta parameter that goes into the Boltzmann exploration. You can choose it different values, and we were interested in sensitivity and like what sort of performance you get across the board if you're choosing these values differently. And you can see that Polytech is not that sensitive, and it's pretty much on par with the other algorithms. So in this queuing problem, so what's special about it, why we're not, so this algorithm, I'm not claiming this algorithm is any clever in doing exploration strategies. It's not going to do the deep planning exploration. The problem that it may not choose some actions that it should choose, because Boltzmann is like, okay, in bandits we can make Boltzmann. It's kind of wonderful. You can make it a pretty good algorithm. For MDPs, it's not so clear that that would be the case. So we're not making any claims about that. We just observe that, like in some problems, maybe you don't need that much exploration. Like in queuing, it seems that the system is kind of exploring everything for you, and like the features are helping you. We have a more precise formulation this in the paper with linear function approximation, but more recent work.
Just a clarification. So the Boltzmann exploration, so this is mixed in on top of the exponential weights. So you do exponential weights, and then after you get that distribution, you do Boltzmann on top of that?
No. I'm confused about what you're saying. Exponential weights to me is Boltzmann.
Oh, okay, that's what you mean by Boltzmann. Okay, so
I mean, it's the same thing. Exponential weighting gives you the Boltzmann policy,
okay.
right?
So it is just on the current estimates is what, there's no like an additional noise you're adding to that?
No.
Okay, fine.
Yeah. Well, yeah, we didn't do any of that. Yeah. Right. Okay. Right. So yeah, like there is, but there are those problems where you need actual exploration, where you need to make an effort to visit places where you wouldn't just randomly get to. So what do you do there? We have a follow-up work where we are attempting to answer this question by introducing another black box. Okay, so we seem to be like, like you can't solve some problem, let's just make it someone else's problem. So they have to worry about this black box, and then once they solve their problem, then I can just take the black box and plug it into my algorithm, and I can have, like this nice Lego world when I'm building up bigger and bigger systems. So it's, separation of concerns, divide and conquer. It kind of works. It may not give you the best possible algorithms, but maybe it's robust, right? Like it's a strategy. So here, what we're saying is that, like, let's imagine that someone is able to build an exploration policy that gets to places, right? Like Sham was working on this, and then there are many other works on curiosity-driven exploration, where they give you some policy whose sole purpose is to get to places. I know the question is, okay, if I plug in this policy, can I use it in some clever way to have low regret? And the answer is, of course you can. If someone hands over a policy like that to you, what you should be doing is that you have to switch back and forth between the policy that you really want to execute and the policy that does the exploration for you. So you let the policy to go to places, and once it got to some place, you also have to make sure that you're trying all the actions there. So you're going to take a random action there, and after that, you just follow your policy. So you kind of do these random resets. You use this exploration policy as a way to reset the system to, like a random state and a random action. And if you do this, you can push it through the math, and then you can get some results. If you implement it, so we implemented Polytech as well, even with neural networks, and we tried in some other games like Miss Pac-Man, and it was working well. And I didn't show you the graphs, but it was actually like noticeably way more stable. I never seen Polytech's reward graphs dropping, so it was kind of going up, and maybe like it goes up and stays up. So if you're running these alternatives like DQN or something like that, then it's like suddenly sometimes it just forgets things. And you know, like that's a little bit worrisome. Like I don't really want to use an algorithm like that. Okay, but if you do this exploration-enhanced version of Polytech, then on problems where you don't need that much exploration like queuing or Miss Pac-Man, it turns out that it just hurts, right? Like you make the system go to places and then it doesn't happen. So there's, that's OK. But in other problems where you really need exploration, I won't have time to explain this. It kind of works.
Wrap up in a few minutes,
Huh?
couple minutes.
Don't you have to kiss a plane now?
I do have to catch a plane, yeah. So I need to really wrap up. So it's kind of weird because I have this mix of different versions of the slides. Anyways, OK. So where are we? So I guess it's kind of interesting to try to decipher of why various ideas that are coming from the deep learning community work and try to use our tools to understand them. So this kind of the inverse analysis, I call it inverse analysis. So someone designs an algorithm and you go in and you say, oh, what is the scope of this algorithm? It cannot work always. Maybe it works sometimes because we see good results. So this work is kind of going into this direction, but it's going a little bit further there because it also says that, well, OK, we can take then the theoretical insights and then turn them into an algorithm. So I think that this is kind of an interesting place to be. So where do we go in the future with this? Well, I didn't talk about, I mentioned some of the challenges with the theory. Well, one of the puzzles is that for bandits, we can really make Boltzmann exploration. We can turn Boltzmann exploration into really good strategy. And for MDPs, that's almost certainly not the case. The question is whether there's something that lies in between. And I don't really have a good answer to that. But that's a very, very interesting question. Also, Boltzmann is not the only strategy that you can use in online linear optimization. Indeed, people have been pushing the limits of how you should do online linear optimization. Maybe you should use some other regularizers. We know that there are bandit algorithms that interpolate between stochastic and adversary averts that just change the regularizer. Maybe we can do the same. All right. OK. So with that, let me thank you for staying that late.
Okay, any quick questions for Shava? OK, if not, I want to thank everybody for coming and have a good trip back. Thanks a lot.